Introduction to Linear Transformation. Intro to Linear Transformation. From now on, linear transformation will be written as LT. If L is a mapping from Rm, well, let's call it Rm, into Rn, that satisfies the two conditions below, then L is not only a mapping, it's a linear transformation. And the two conditions are as follows. First, let's set the premise. Let U and V be in Rm. You take L of things in Rm, and you get things in Rn. And C is any scalar. L of U plus V is equal to L of U plus L of V. That we'll call condition 1. Condition 2 is L of C times U is C times L of U. If those two conditions are met, the mapping L is a linear transformation. By the way, we call most linear transformations L. I guess if you have two linear transformations or three in a given problem, you'd call them L, capital M, and capital N. Of course, you can call them A, B, C. You can use little letters if you want, lowercase letters, whatever you choose. But generally, you start with the letter M. Okay. Now, let me give a mapping, and the problem to be to decide whether or not this mapping L is in fact a linear transformation. If L is a mapping from, I want to make a comment before we go on. I guess I could have left what I started to write. Remember I said is a mapping from Rn into Rm, or Rm into Rn. If L is a linear transformation and N and M are equal, we can also call L a linear operator. If L is a linear transformation and N and M are the same number, then we can call L a linear operator. We can call L a linear operator. Just definition. Okay. That we let L be a mapping from R3 to R2 be defined by the following. L of xyz is yz. This is a projection of R3 onto the yz plane. So the question is L a linear transformation? Is L a linear transformation? Well, you have to verify condition 1 and 2 of the definition. Let u equal to, say, x1, y1, z1, and v is equal to, say, x2, y2, z2. Now, u plus v, vector u plus vector v, as always, add the first components of u and v, comma, add the second components of u and v, and add the third components of u and v. And why am I doing that? Because I want to see what L of u plus v equals. I want to see if it's the same as L of u plus L of v. I want to see if L is linear. So I'm really taking L of this mess. x1 plus x2, y1 plus y2, z1 plus z2. And what I get is the last two components. That is the first component in R2, because I'm going into R2. The first component into R2 is the second component of what I'm taking L of. I'm taking L of what's in here. I get the second component first. And then the third component goes second. But now, I want to get that this is ultimately L of u plus L of v. That's my goal. But L of u will be y1, z1. L of u of this will just be y1, z1. Plus L of v, why that's z1 plus z2. But this equals the line above. That is, if I didn't do this, I'm going to do it again anyways. But if I didn't do this, this vector in R2 is the same as y1 comma z1 plus y2 comma z2. That is, it is L of u plus L of v. So yes, L of u plus v really is L of u plus L of v. Okay? We have condition 2 that we have to verify. Okay. Let C be a scalar. U. I'll use the same U as the last part. So then I get C times U. Oops, I used x1, x2, x3 for U. So I get C times x1, comma, C times x2, comma, c times x3. And L of anything in R3 is, first you write down the second and then a comma, and then you write down the third entry. The second entry, comma, the third entry. But this is just a vector. Nothing to do with linear transformations. This is a vector in R2. And C is common. I can factor it out. Well, C is C. This is, well, remember, U is x1, x2, x3. So L of U, that is L of this, is just x2, x3. But that's what I have here, x2, x3. That's just L of U. L, therefore, this wasn't a proof actually, therefore, L is a linear transformation. Why? Because we satisfy condition 2. Previously, we verified condition 1. If 1 and 2 are met, so L is a linear transformation. If any one of them is not verifiable, it fails, then we say L is not a linear transformation. Not all mappings are linear transformations. You can have a mapping from set A into set B. No. Goes from R2 into, Rm into Rn. And it has to be not just any old mapping from R into Rn. It has to be linear. It has to satisfy those two conditions. Okay, so suppose we have another one. Suppose we have is a mapping from R3 to R2 defined as follows. Defined by L of V1, V2, V3 is equal to, I don't know, the second component plus 1, the second component plus 1, comma, because I have to be in R2, I have to write two things, and then we'll say the third minus the first, V3 minus V1. That's how L is defined. Okay. U2, U3, and V is equal to V1, V2, V3, and C is an element of the real numbers. C is any scalar. I ran out of room, so I wrote it that way. C is a real number. That is, it's a scalar. Okay. All right, so plus V. Well, U plus V is U1 plus V1, comma, U2 plus V2, comma, U3 plus V3. And what L does to any triple is it takes the second one and it adds 1 to it. Okay? I'm not going to discriminate. I'm going to take the second entry and add 1 to it. And then, for the second entry, it's the third entry minus the first. It's the third entry, U3 plus V3, minus the first entry, U1 plus V1. That's what L of U plus V is. Now let me just do a little arithmetic here, a little algebra. You have U3 minus U1. plus v3 minus v1. No, v3 minus v1. Okay. Now, what's going to fail here is that 1 plus 1 is not 1. Over here, we're adding 1. Now, if you look at L of u plus L of v, L of u is the second component plus 1, comma, the third component minus the first component, u3 minus u1. That's L of u. Plus L of v. L of v is the second component plus 1. And then the third component minus the first component. The third minus the first. Now, when you add these together, first you add the first components. And you're going to get u2 plus v2, and then u2 plus v2, and also 1 plus 1. The problem is 1 plus 1 is not 1. It's 2. And when it comes to the second components, you get u3 minus u1 plus v3 minus v1. Just like we got over here. L of u plus v is this. And if you notice, the second component here, the second component here are equal. But the first one is not. This here is u2 plus v2 plus 1. This is u2 plus v2 plus 2. When you take L of one thing, you take that second entry and you add 1 to it, and that becomes the first entry of their element in R2. But over here, take L of u, you get a plus 1. Plus, now when you take L of v, you get another plus 1. And when you add those ones, you don't get 1 anymore. You get a 2. It failed. Okay, I should write, say right here, since, of course this should be on the bottom, since L of u plus v does not equal to L of u plus L of v, L is not a linear transformation. That should be at the bottom. So here's an example where L is a mapping, but it's not a linear transformation. Okay. All right. So now let's try one more. Suppose L is a mapping from R3 to R2 once again. The reason we like R3 to R2 or R3 to R3 or R2 to R3, it's not that many numbers. We don't want to deal with R72 because that means we have to go out to we have to have 72 entries to define a vector in R72. Here is in R3, 3 numbers. And suppose it goes to R2, which is just 2 numbers. And let this mapping L be defined by L of a vector u, and L, you take L of things in R3, so vector u is understood to be in R3, and you get R times the vector u, and this is for some scalar R, And of course, we have a mistake going, because if you have a vector in R3, and you multiply each entry by R, you still have a vector in R3. So L is a mapping from R3 into R3. Now the question is L a linear transformation? L of U plus V, U and V are in R3, and this becomes L of any vector is that vector, and when you add vectors U and V, you get a vector, and L of any vector is R times that vector. And we know some properties about sums of vectors. We could scale each of those vectors, R times vector U and R times vector V, and then add that up. But wait a minute, R times U, R times R is the key thing here. R times any vector is L of that vector, plus R times V, well, that's L of V. So here it's linear and over addition. You can take L of U plus L of V. You really were able to. Now, let's look at L of C times U. Now, C times U, a scalar times a vector, is just another vector. If C is 1, it's even the same vector. C times U is some vector. There it is. And L of any vector is that same vector times R. Now here is where you have to know your theorems and know what these objects are. R and C are scalars. There's a theorem that says you can bring the scalar in front of the vector. R and C are real numbers. And real numbers commute. You can switch to R and C, times it by U. And just like you were able to bring the constant in front or the scalar in front, you can put the scalar back in. This is C times RU. Now C is C, and R times U. R times any vector, in this problem at least, is L of the vector. So here you really were able to bring the C out. And in this proof of our properties 1, or verification of properties 1 and properties 2 of the definition of linear transformation, I never even have to say that U is U1, U2, U3. And please remember, although I might be writing the vectors horizontally, V1, V2, V3, I can always choose to write them vertically. So this is a linear transformation. Now, what exactly does this linear transformation do? Does it do anything that we can understand? Earlier, though we didn't talk much about it, we had a linear transformation that was a projection onto the YZ plane. And if I said YZ axes earlier, I meant to say plane. Now, the vector U gets scaled. If R is equal to 1, then L of U is 1 times U, which is U. That is, it doesn't do anything. In other words, if this is the vector U, then if R is 1, L of U gives back the same exact vector. Gives back the same vector. Here's a number line. So we talked about what happens if R is bigger than 1, then the length gets the length is now longer. That's r times u, if r is bigger than 1. Well, what if r is positive but less than 1? What if r is between 0 and 1? So if this happens to be the vector u, well then r times u would just be not as long. Maybe it would just be that portion. If r is a half, well then it's half as long. If it's r is 3/4, it would be 3/2 as long. All right. Now if r is 0, 0 times the vector will be the 0 vector. So, if u starts at the origin, if it doesn't, just move it to the origin. If u starts at the origin, then L of u, if r is 0, L of u would just be that one point. It starts and finishes right there. Now, if r is negative, that just means that if u goes this way, then a negative times u would just go that way. Now, if r is negative 1, then these two vectors will have the exact same lengths. They will have the exact same lengths. The vector head doesn't seem to want to come out nicely. Now, if r is bigger than 1, if r is less than negative 1, that would just mean that u, remember u was this vector, the new vector will go in the opposite direction, and it'll be longer than the original vector u. That's if r is below negative 1. If r is between negative 1 and 0, then it would be shorter. It would start at the same place as u started, but it'd go in the opposite direction, but not quite as long as that. A little bit shorter, maybe almost as long, like what if r was almost 1, 0.99999? Be almost 1. So to be almost as long, just ever so slightly less. So that's what this vector is doing. It's making, that's what L is doing. It's making every vector longer or shorter or in the opposite direction. Longer than u or less than u. And if r is 1, you get back exactly u. If r is negative 1, you get back the same lengths but of u as u, but in the opposite direction. So sometimes these linear transformations have very solid meanings, very exact meanings. So how about we prove our theorem? If L from Rn into Rm is our linear transformation, then L of C1U1 plus C2U2 all the way up to CNUN. Notice, okay, up to CNUN. No, I don't like using N. I was thinking for a moment that it would have to be that number. But no. Each U1, U2 up to wherever, those will be vectors in Rn. see what's a nice letter. We use UR, CR, UR. CR, UR. And this is going to equal to, put it down, L of C1U1 is linear, C out in front, plus L of the second vector, and that the C2 can come out in front, all the way down to L of this vector, which is CR, L of UR. You can't be any more linear than that. But we need to prove this. This is a proof by induction. By induction. If anyone, if R is 1, I'll use the letter R. R is equal to 1. Well, then I write down both sides, but I stop when R is 1. That is, I get this piece. Get this piece. L of C1U1. If R were 2, well then I would get this. Stop when the subscript hits 2. And this is supposed to equal to this line over here, but I stop when R is 1. That's right there. And of course this is true. Why is this true? By definition of our linear transformation. Linear transformation says if you have L of a scalar of any vector, you could pull out the scalar. And that's all I did. So this one is true. Now we assume for R equals K. We claim this is true all the way up to R equals K. That is L of C1U1 plus C2U2 all the way up to CK that this is nothing more than C1 L of U1. That is, it's L of this, but the C1 can come out in front, plus L of this vector. And the C2 can come out in front, plus all the way down to L of CK But in linear transformations, the constant comes out in front. The question is can you take L of this plus L of that all the way up to L of CK? If you can, well, yeah, certainly then you can pull out the scalars. Now we must show that it's true when R is 1 more than K. That is, I just stop at 1 more than K. I stop at K plus 1. That is L of C1U1 plus C2U2 all the way up to CK plus 1 UK plus 1. This is equal to, you want to show this, C1 L of U1 plus L of this, which is C2 L of U2, all the way down to L of this, the constant or scalar comes out in front, times L of UK plus 1. We want to show whether or not this is true. We want to show whether or not that is true. Either it is or it isn't. Okay. Now, in mathematics, when you have a sum of many things, if you want, you can think of it as just one thing. For example, if you're adding vectors, v1, vector 1 plus vector 2 plus vector 3 up to vector 25. You can think of those as 25 vectors, the sum of 25 vectors. Or you can think of it as one vector. After all, when you add those 25 vectors, you get one vector. If you tell me that 2 plus 3 is two numbers, I will most definitely ask you, what two numbers? 2 plus 3 is one number. It is the number 5. It's one number. I have to think of 2 plus 3 as one number. It's the sum of two numbers, but it's also one number. If you have 2 plus 3 plus 4, it is most certainly the one number 9. But if you want, you can think of it as 2 plus the number 3 plus 4. You can think of it as the sum of two numbers, 2 and 3 plus 4. 3 plus 4 is one number. You get to think of it however you need to have it. If you need to have a string of 20, the sum of 20 vectors to be two vectors, well, you can take the first 19 and think of that as a vector and add that to the 20th vector. Now you're adding 20 vectors. Or you can take the first vector and add it to the last 19. Where the last 19 vectors being added, you think of it as one vector. Okay, so we must show that this is true. L or C1U1 plus C2U2 all the way up to CK plus 1, UK plus 1. But the term before that will be CK, UK plus CK plus 1, UK plus 1. Now, a little bit more space, L of this sum. L of C1U1 plus C2U2 all the way up to CK, UK. Now think of that as one vector. So that went up to here, plus that vector, plus CK plus 1, UK plus 1. Now, why do I want to do that? Why do I want to do that? So the next step, that it's this first vector. Second, I'll tell you why we want that. So L of the first vector plus L of the second vector. Now, oops, I didn't write L. Plus L of the second vector. Now, the reason we want this, sometimes or lots of times in mathematics, you have to see the future, have to see ahead. Well, L of this, that we assumed something about that. We assumed that L of this is equal to that. That is taught. L of that is C1L of U1 plus C2L of U2 all the way up to CKL of UK plus this. But L of that is CK plus 1, L of UK plus 1. The scalar can come out in front. And that's exactly what I wanted to prove. I wanted to prove that. Now, this is pretty powerful stuff. Before we look at a numerical example, I want to prove another theorem. That way we can talk about L of U minus V. That is, you don't just have to compute L over sum of many vectors. you can have L of vector A plus L of vector A plus vector B minus vector C plus vector D minus vector E. They don't all have to be plus. So let's get this theorem out of the way. Back statements. Let L be a mapping from Rn to Rm, which is a linear transformation. Then the following is true. L of the zero vector is equal to the zero vector. And part B says L of u minus v, u and v are vectors, is L of u minus L of v. Now, before we go on, I realize there's one little thing that I should have said earlier on that I just want to say. Let's see if I can find it. I think there was a mapping from R3 to R3 that was a linear transformation. And I just want to say that it was also a linear operator. Yeah, this one. Since L was a linear transformation, we proved it, from R3 to R3, we could have also said that L is a linear operator. Minus statement I just wanted to include. Okay. Now, before we prove A, let's look at A a little bit more closely. Let's look at A a little bit more closely. You take L of things in Rn. So the zero vector, the one that I'm taking L of, it must be in Rn. And when you take L of things in Rn, you get things in Rm. And I'm taking L of something, and what I'm getting must be in Rm. Now, if n was equal to 2 and m was 3, well, what I'm saying is L of the zero vector in R2 gives me the zero vector in R3. Okay, these two vectors are not equal. The zero vector in R, unless n and m are equal, the zero vector in Rn is not the same as the zero vector in Rm. Again, if m and n are equal, then yeah, they are the same zero vector. Each vector space has its own zero vector. Okay, so having stated that, let's prove this. Now remember, every vector has an additive inverse. If you have a vector in R3, 7, 2, negative 4. There is a vector that you can add to it to get back the zero vector. 7, negative 7. 2, negative 2. Negative 4, positive 4. When you add those two numbers, you get 0. When you add those two numbers, you get 0. When you add, because we're adding, when you add those two numbers, you get 0. Okay? So every vector has an additive inverse. Now, the zero vector in Rn is certainly equal to the zero vector in Rn. So here's the zero vector in Rn equals the zero vector in Rn plus the zero vector in Rn. You add the zero vector to itself, you get back the zero vector. L of the left side is equal to L of the right side. Zero vector plus the zero vector. But L is linear. I have, on the right side, I have L over sum. I have L over sum. And hopefully you see what's going to happen. The right side, I have L over sum. Left side didn't change. The left side is still L of 0, but the right side is L of 0 plus L of 0, because L is a linear transformation. So L of the 0 vector in Rn is equal to L of the 0 vector in Rn plus L of the 0 vector in Rn. L is linear. Okay. But each of these vectors are in Rn. This vector, L of the 0 vector, is in Rm. L of the 0 vector is in Rm, and L of the 0 vector is in Rm. When you take L of anything, in Rn, of course, you are going to get something in Rm. All right, so now I'll take away I'll take away L of the 0 vector. If you prefer, okay, I'll take away L of the 0 vector. I'll take away L of the 0 vector. Remember, u minus u is the 0 vector. Maybe I should have said that instead of additive inverses. Sorry. Okay. The left side, you have a vector in Rm, and you're taking away the same vector in Rm. So you are going to get the 0 vector in Rm. On the right side, this is the 0 vector, just like it was on the left side, and L of any vector, including the 0 vector, L of the 0 vector plus the 0 vector is L of the 0 vector. And I copied this down wrong below. The subscript should be, or the superscript should be Rn. So I proved it. L of the 0 vector is equal to the 0 vector. Pretty neat. Okay. So it's always the case that when you take L of the 0 vector, you will only get the 0 vector, or always, excuse me. Of course, you're only going to get one vector, because it's a function. But you will always get the 0 vector. L of the 0 vector is always the 0 vector. Not the same 0 vector you started out with. When you take L of the 0 vector in R3, for example, and you get the 0 vector in R5, those 0 vectors are not the same. Okay, now we want to prove B. And we have L not over sum, but we have L of a subtraction. And we don't know how to take L of a subtraction, but I think for a moment, how can I write u minus v as a sum? Well, think of u minus v as one vector and add something. I'll add v. If you have u and then you take away v, but you quickly add v back, you'll have u. You'll have u. So now I take L of both sides together. U is L of u minus v plus v. It's a sum. It's L of this plus that. So L of a sum is L of, in this case, u minus v, and I plus L of v. And I just love seeing this, because I want to know what that is. And the left side is just L of u. Well, I only want to have L of u minus v. I want to know what that is equal to after all. So I'll take away L of v, and the right side is just L of u minus v. And I will do the same on the left side. I will take away L of v. So I get L of u minus L of v. And that's exactly what I wanted to show. L of u minus v is L of u minus L of v. It's not because somebody told you this was true. We proved it. And I don't know how well I said this, but it's very common in mathematics. If you do subtraction and somehow you want an addition, is to realize the addition that way. Okay, that's a very friendly way of doing it. Other times is if you have u minus v, or if you have a minus b, you can think of it as a plus negative b. So now we can look at some examples. I think before we proved that L of u minus v equaled L of u minus L of v, it would have been premature to do examples. Now, before we even do an example, I just want to make a comment. When we defined, some of you may be saying, you know, what is going on? How come when we defined a linear transformation, we didn't have three properties? You know, definition of linear transformation. So mapping from Rn to Rm that satisfies L of u plus v. L equals L of u plus L of v. L of u minus v is L of u minus L of v. And C times L of u is equal to, L of C of u. L of Cu is C times L of u. Why didn't we add in the second one? It's a very, very, very simple reason. In mathematics, you want your definition to have as little as possible. We don't need this one. Why don't we need this one? Because we can prove it's true. The greatest definition of linear transformation would be, yes, L is a mapping from Rm into Rn that satisfied L of C1U1 plus C2U2 all the way down to Cn or Un is equal to C1 L of U1 plus C2 L of U2 all the way down to Cn L of Un. That would have been the greatest definition. But in mathematics, we want to say the least. And the least is 2. That's the least. Why would this definition have proved both of these? Well, if n was 1, then we would have just said L of C1 U1 is equal to C1 L of U1. And if we looked at just 2, L of C1 U1 plus C2 U2, this is supposed to equal to, let's just use 2 of them, C1 L of U1 plus C2 L of U2. Well, if C1 was 1, 1 times U1 is just U1. And if C2 was 1, 1 times u2 is just u2. And whatever L of u1 is, 1 times it is just L of u1. Same thing here. So we have it. L of u1 plus u2. In the definition, I use u and v. Nonetheless, L of u1 plus u2 is L of u1 plus L of u2. You know, you may say, well, that's short. This definition at the very bottom, it only has one thing. Well, we also want it to be more compact. I myself would also have defined the definition of a linear transformation using what I have at the top being 1 and 3. I would have defined myself linear transformation this way without L of u minus v. It's unfortunate. If you look at a more serious, more rigorous mathematics book, possibly even just Google it on the internet, but if you look up the definition of a square, it does not have to say all angles are right angles. If opposite sides are parallel and all 4 sides are equal, you just need one right angle. You can prove that the other 3 are right. Okay. Now, suppose L is a linear transformation from R3 to R2. This is a linear transformation with the following. You know, where we know that L of 1, 0, 0 is 2, 3, and L of 0, 1, 0 is 3, 4, and L of 0, 0, 1 is 5, negative 3. Okay, so we know that. And L of 1 or 4, negative 4, 3. We want to find L of 4, negative 4, 3. Well, 4, negative 4, 3. This is 4 times 1, 0, 0. Because that just contributes to a 4 in the first entry. So I got my 4, and I won't touch it. Because I'll now take away 4 times 0, 1, 0. And 4 times 0 is still 0. It didn't touch my 4. But I get a negative 4. Here, the second entry, let me write them all down. Plus 3 times 0, 0, 1. Notice the 4, the negative 4, and the 3. That was exactly what I want to take L of. When you FOIL it out, the first one only puts the non-zero entry in the first position. Minus 0, 4, 0. Minus 4. And it gives you 0 in the other positions. And lastly, the first 2 positions are 0, but then you get a 3. Plus 3. And when you add or subtract, combine, let's say, you do get that. Okay. We talked about how you can do that earlier. Now, I want to find L of 4, negative 4, 3. L of 4, negative 4, 3 is equal to L of this. It equals to L of that. 4 times 1, 0, 0 minus 4 times 0, 1, 0 plus 3 times 0, 0, 1. Okay. But this is our theorem. Our updated theorem, because now we can do the same thing even if you have a minus. This is L of this. The 4 comes in front. If you want, I'll write it down the long way. Minus L of this. But the 4 comes in front. L of 0, 1, 0. Plus L of this vector. But the scalar can come out in front. But the nice thing is I know L of each of these. 4 is 4. And L of 1, 0, 0 is, you got it. It's 2, 3. Minus 4 times L of this, which is 3, 4. Plus 3 times L of 0, 0, 1, which is 5, negative 3. So I'm going to get something in R2. First entry will be 8 minus 12, which is negative 4, plus 15 is 11. And then you get negative 12 minus 16, which is negative 4, minus 9 more, negative 13. So there it is. There it is. And I don't even know the definition of the linear transformation on the top. Don't even know the definition of it. Don't know the definition, but yet I can still do it. Let's look at another problem. Here, you were given their, what did we call those earlier? We call them E1, E2, E3. We call them, in R3, we call them the I, J, and K vector. But we also call them the unit vectors in the I direction. That was 1, 0, 0. And a unit vector in the J direction, which was 0, 1, 0. And vector K, which was a unit vector in the Z direction, which was 0, 0, 1. But what if we don't have that now? What if we're told that L is a mapping, say, from R3? We'll go to R2. Actually, let's just make it a little simpler. Let's go R2 to R2. R2 to R2. And we come to know, we're given that L of 3, 2 is 5, 1, and L of 4, 0 is 4, negative 4. Suppose we have this, and we want to find L of, see what a good thing will be, L of 2, 6. So basically, we want to write 2, 6 as a linear combination of 3, 2, and 4, 0. That means we take some multiple of 3, 2 plus some multiple of 4, 0. Now, if you want to use matrices, you can. And after all, this says that 3 alpha plus 4 beta, alpha times 3 or 3 alpha plus 4 beta, this must equal to 2. And the bottom one says that 2 alpha plus 0 beta, it must equal to the number 6. And that corresponds to this system of equations. 3, 4, 2, and 2, 0, 6. 2, 0, 6. Now, you can solve this using elimination techniques, and you will 100% get the right answer. But rather than using matrices, I think it's a bit easier to realize from this second equation at the bottom right that alpha is 3. After all, 0 times beta is 0. So 2 alpha plus 0 is 2 alpha. It equals 6. 2 alpha is equal to 6. Well, I'll jump on that. I mean, I can look at this equation and say alpha equals 3 immediately, because that's 0. Okay, So now we come to the first equation. 3 times 3, because alpha is 3, plus 4 beta is 2. This must be negative 7, because 4 plus negative 7 is 2. So 4b is negative 7. So b is negative 7 quarters. Okay, b is negative 7 quarters. That is 2, 6 is equal to alpha, which is 3, times 3, 2, plus beta is the same as minus 7 quarters, times 4, 0. So, L of 2 is equal to L of the right side, which is nothing more than L of this, which is 3 times L of 3, 2, minus L of this, which is 7 quarters times L of 4, 0. But I know those L's. I know what L of 3, 2 is. I know what L of 4, 0 is. They gave it to me. It's the second line from the top. They outright told me what they were. I'm going to jump on that. You tell me what something is, I will believe you. It amazes me how students will be given something. They will be told x is equal to 3. And in the end, or somewhere along the problem, they will plug in 13 for x. Or, they'll say x equals 13. No. If you're told x equals 3, don't deviate from that. So this is 3 times L of 3, 2. But L of 3, 2 is 5, 1. Minus 7 quarters times L of 4, 0. L of 4, 0 is 4, negative 4. Okay, so what we get is 3 times 5 is 15. 3 times 1 is 3. Minus, when we distribute the 7 quarters times the 4, you just get 7. And when you do 7 quarters times negative 4, you get negative 7. And as always, the very, very last line, I run out of space. So let me put it right above, and this problem will be history. Minus 7 is 8, and 3 minus a negative 7 is 10. So the answer to this is 8, 10. L of 2 6s, 8, 10. So this theorem that we proved earlier, and then we updated it where we say that it even works when we're taking away vectors, not just always adding many, many vectors. Pretty nice theorem. We can do things without even knowing the linear transformation. Okay. Now, I'm going to do something very exciting. At least I think this was exciting when my linear algebra teacher put it on the board. I didn't really see, this is pretty sad, but I didn't see exactly where my professor was going with it. But I knew it was major. I was sitting on the edge of my seat. I knew something very interesting was going to come up very soon. Okay. Now we let L go from R2 to R3, and it's defined by then in R2 is equal to 731,425 times xy. Okay, so is we should verify one thing. I'm claiming that xy, well, I'm supposed to take L of things in R2, and xy is certain. Let's just make sure that I am getting something in R3. Well, if you were to multiply these two matrices, you would get 7x plus 3y, 1x plus 4y, and then 2x plus 5y, which is in R3. And it had nothing to do with what those numbers were. It had to do with the fact that there were 3 rows and 2 columns. Had nothing to do with what those numbers were. Whatever these numbers were, when I dot it with the first column, I will get an entry in the first row. When I dot the second row with the first column, I will get something in the second row, first column. And when I dot the third row with the first column, and the only column, I get something in the third row, first column. Those numbers didn't really matter. In fact, I'm even going to erase this. Okay. So the question is this a linear transformation? Is this a transformation? Maybe it is, maybe it isn't. So let's take L of a sum of two vectors. Say xy plus x prime y prime. Let's take L of that. Now, L of any vector is this matrix times the vector that we're taking L of. That is, this is 7, 3, 1, 4, 2, 5 times xy plus x prime y prime. I want you to notice we're not going to do anything with that matrix. In other words, if at some point I said, oh my, what a big mistake I made, that 3 was really an 8. It won't even matter. Okay, now, when you have a matrix times the sum of two other matrices, this is a vector, but it is also a 2 by 1 matrix. And n by 1 matrix is a vector, and it's a matrix. You can distribute the A. This is AB plus, and if that was minus, I would write minus there, AC. In other words, it is this matrix times xy, 7, 3, 1, 4, 2, 5, times xy, plus that same matrix times x prime y prime, times x prime y prime. Right? Now, that matrix times any vector is L of that vector. L of a vector is that matrix 1, 4, 2, 5 times a vector. So that matrix times xy that you see on the bottom left, that's L of xy. That's L of xy. Plus the other plus that same matrix 7, 3, 1, 4, 2, 5 times x prime y prime. That's L of x prime y prime. This here, this matrix times any vector in R2 is just L of that vector in R2. Plus this matrix times any vector in R2 is just L of that vector. It'll work like a charm. Regardless of what this 3 by 2 matrix was, it worked. Again, if I say, oh my, I made a silly mistake, this 3 was really an 8. It's not a big deal. I'll change it to 8. It isn't like we used this 3 and now it's, it's jumbled in somewhere and it's no longer a the matrix never changed. All right. Now that was condition 1 of the definition. Now, let us look at condition number 2, the scalar multiple condition. Now, let u equal xy, and c is any scalar. Well then, L of cu is just L of cu, which is c times xy, because that's u, and c times xy is cx cy. And L of that, L of anything, is this matrix. Whether it's a 3 or an 8 doesn't matter. Times, no, I don't even want to say this middle step. I don't even want to say this, that c times xy is cx cy. I can do the proof saying it, but it's not necessary. L of any vector in R2 is this matrix 7, 3, 1, 4, 2, 5 times, you know what, I don't even need this. I don't even need this. I don't even have to say that u is xy. But u better be in R2. So I can only take L of things in R2. Okay, what L of anything is this matrix. Is this matrix times cu. Times cu. And maybe I will now say, yep, I should say that u is not a vector, but actually write it as a matrix. It's a matrix xy. Now, we had a theorem that if you had A times RB, you can pull the R in front. This is R times A times B. Oh, you know, this is A, that's my R, and that's my B. This is the same thing as C times, oops, that matrix, 7, 3, 1, 4, 2, 5. 7, 3, 1, 4, 2, 5 times xy. And this is C, that's C, and that matrix times any vector is L of that vector. And another name for that vector is U. Yep, the C comes in front. Therefore, L is a linear transformation. L is a linear transformation. Again, there was nothing really special about that matrix. More generally speaking, there's nothing special about it being from the linear transformation going from R2 to R3. It didn't matter. It didn't matter. So what we can say, we can make this statement in general. Okay, we can generalize this in general. And then I'll really say a much stronger statement. In general, let A be an M by N matrix. Then L that goes from, I think it's Rn into Rm. Well, first let me make that an M. And then let's look at the last problem for a moment. Let's look at a last problem. We are going from R2 to R3. But yet the matrix, this matrix down here is a, let's see, it's a 3 by 2. That is the size of the matrix, you have to switch the m and the n. If L goes from R2 to R3, you don't need a 2 by 3 matrix, but a 3 by 2 matrix. And this is true in general. Okay. Then you get caught up in L from Rn to Rm defined by L of x in Rn by 8 times x is a linear transformation. Okay. Now, here's our image. Well, since I have what I have right above it, this A above is unique. There's only one matrix A for a linear transformation. Okay? No, what I said is true, but there's a much, much stronger statement. There's a much stronger statement. Let me think how to word it. Let L be the mapping from Rn to Rm be a linear transformation. Okay? It can be defined by L of xy is equal to x minus y, x plus y. That is, no matrices. No matrices. Let L be the mapping from Rn to Rm be a linear transformation. Then there exists a unique n by n matrix A such that L of x is equal to AX for all x in, well, you take L of x, you take L of things in Rn, for all x in Rn. Okay. That is, this is always true, not sometimes. Okay. So now, how do you find this matrix A? How do you find it? Now, your teacher will tell you to find L of the E's. Find L of E1, and L of E2, and L of E3. And then whatever L of E1 is, put that answer in the first column of A. And find L of E2 and put that answer as the second column of A, etc. All the way down to find L of En and put that in the nth column of matrix A. And that works, absolutely works. But there are easier ways of doing this. Suppose L is a mapping from R3 to R3 And it is a linear transformation defined by L of a vector in R3, call it x, y, z, and we get back, say, 3x minus 4y, 2y minus 3z, and 3x minus 4z. Okay, well, I want to write this as some matrix times the vector x, big X, which is little x, y, z. It's very simple. This is a times x, y, z. What you do is you put x, y, z up here, just as you see it in that order. First x, and then underneath it is y, and underneath it is z. Just write it horizontally. In the end, you could erase this. This here, it has 3 x's. This here has minus 4 y's, and it has no z's. This second row, it has no x's, positive 2 y's, minus 3 z's. And this here has 3 x's. It could have had y's, but it doesn't. And it has negative 4 z's. That's it. That is your matrix A. And if I didn't state it, the problem is saying find the matrix A so that L of x, y, z is equal to A times x, y, z. And if you actually multiplied A by x, y, z, you will get this. Actually do it. Make sure I didn't make a mistake. Let's try one more. It's really simple to find the matrix A with a linear transformation. It is not hard at all. So let F be a linear transformation. It goes from R4 into R2. L is a linear transformation defined by L of something in R4, L of x, y, z, w, and I'm going to get something in R2. That is, I'm just going to have 2 rows. The first row is 3x minus 4z plus w, and the second row is 3x minus 4y plus 2w minus z. Now I want to write A. I want to write this as some matrix times x, y, z, w. Whether you write up here x, y, z, w, that's up to you. But you need to think it. And by the way, in the end, you really should erase it. Okay. This first row, it has 3 x's, no y's, negative 4 z's, and 1 w. The second and last row has 3 x's, negative 4 y's, 2 w's, and negative 1 z. I found my matrix A. It's done. It's much easier than finding L of, let's look at L of 1, 0, 0, 0. Okay, but first I have to write it vertically. What is L of? Okay, well, only x is 1. So, if only, and the rest are 0. So this is just going to be 3. This is just going to be 3. And the second entry, if only x is 1, 3 times 1 is 1, and everything else is 0. So you get 3, 3. Exactly like we got. If you were to look at L of 0, 1, 0, 0, notice only y is 1, and everything else is 0. Well, the first entry has no y's, so I'm going to get 0. The second entry this is the only term that won't give you 0. It'll give you -4. 3 times 0 is 0. 2 times w, which is 0, is 0. Minus 0. The only thing that didn't give you a non-zero term is the 4y. It says to take away 4 ones. And that's exactly what the second row is. And you could find L of E3. You can find L of 0, 0, 1, 0. And I'll tell you what you're going to get. You're going to get -4, 0. It is much too long to do it this way. But you can. And you might have to do it if your instructor says, find A by finding L of E1 and L of E2 and L of E3, etc. Then you have to do that. But my advice is, if somebody told me to do that, I would do exactly what I did. I would do exactly what I did. I would do exactly what I did. Okay? And then I would do what the teacher said. I'll find L of E1, L of E2, L of E3, and I'd even be nice enough to find L of E4. But I already had the matrix. Before I even found the L's. The L of E1 and the L of E2, etc. So you don't have to do that. Your teacher will never know that you didn't do that. Never, not in a million years. Should think about why that would even work. Okay. Now, onto something that would seem that it's in the wrong place. Why is it in this chapter or section on Introduction to Linear Transformations? Cryptography. That probably should be a P. C-R-Y-P. T-O-G-R-A-P-H-Y. Cryptography. So, you want to send a message to somebody. In the past, it would be you want to send a letter to somebody. These days, we should say you want to send an email. I guess even I'm outdated. I should probably say you want to send a Facebook message. You want to send a message that math is fun. Math is fun. And what you can do is, you can write down every letter of the alphabet. A, B, C, D, E, F, G, all the way down to X, Y, and Z. And what you can, and there are 26 letters in the English alphabet. And you can put 1 here, and 2 there, and 3 there, and 4 here, and 5, all the way down to 26. Okay? And if you want to send the letter E, you would write 1. And if you wanted to send the letter X, you would write 2. And if you send like a 3-page message, this can easily be decoded because there's something called a frequency table. And although I don't know it offhand, they know that A, B, C, D, up to Z. They know that, and I'm making up these numbers, they know that the letter A comes up 11% of the times, and the letter B comes up 3% of the times, and that the letter C comes up 11%, 4%, and 1%. Total of 100%. They know this. So now, they notice that the number 20, in your 4-page message, or in your 3-page message, they noticed the number 26 came up 4% of the time. Oh, 26 is D. That is, they don't know this code. They don't have this code at all. They just have 1, 7, 3, 26, 4, 3, 1, 21, 18, 11, 12, 13, 4, 7, 2, 1, 1, 1, 3, 4, 11, 29. Well, no 29, but, 23. They have 3 pages of this number. And they noticed that the number 26 came up 4% of the times. So they conclude that 26 is D. Now, let's make this different than what I have for C. Suppose A comes up 21% of the times. So now they notice that the number 3 21% of the times. So now they know this 3 is A. So they can easily, if they continue with this process by the frequency table, they can decode this message. And you may say, well, I'll get around that. I'll write it in a different language. I'll write it in Swahili. Well, they can find the frequency table for Swahili. It's not going to help. So you want to code it some other way. You want to code it a different way. Okay. So what you're going to do is, and remember, when you multiply something by a matrix now, it's a linear transformation. Okay. Suppose you use their initial code that I said at the beginning. A is 1, and B is 2, and our C is 3, all the way down to Z is 26. We're going to do, oops, that didn't come out. Okay, A, B, C, up to Z. And now it'll write B, C, all the way up to Z. And whenever you want to write A, you write 1, and B, you write 2, and C, you write the number 3. Whenever you want to write Z, you write the number 26. I've actually worked this out. This is 13, 1, T is 28. So let me just spread it out a little bit more, please. Math is fun. M is 13, A is the first letter, T is the 20th letter, H is the 8th letter, of course. If H is the 8th letter, I is the 9th letter, and then the 19th letter, and the 6th letter, and the 21st letter, and the 14th letter of the English alphabet. Okay. Now, you sent that message to one who has a little free time, can break the code, can figure out 13, 1, 28, 9, 19, 6, 21, 14 is math is fun. It's really not that hard. Personally, I never ever broken a code before, but if you give me the frequency table and a big message, a 3-page or letter, not just math is fun, okay? You give me a 3-page letter, I'll break the code pretty easily by just using the frequency table. All right. And now, I can take this message, which has 9 entries, 1, 2, 3, 4, 5, 6, 7, 8, 9, and write it as a matrix. Well, let me not do that. I can take M120 that is these three, put it as the first column. The next three, put it as the second column. The next three, put it as the third column. And whatever, even if you wrote more, every 9 letters would be figured out, decoded in the way I'm about to say. What you do is you take this vector, think of it as a vector, and you multiply it by some matrix. So this is what you want to send. Want to send. You want to send math is fun. Well, I don't want to say that because this is not what you want to send. But this is math is fun. Math is fun. Now, you multiply by a matrix that has an inverse, a non-singular matrix. Okay? You multiply it by that. And the person is going to receive this message. Okay, this product is what you are going to send to your friend. And let's see, it's going to be 34. 17 and 19 is 36. And then it's going to be 20 is going to be 41 here. This is easier. 21, 28, 35. And the last one is 33, 27, and 20. This is the message the person is going to receive. But this is gibberish. Because when they look at the 21st letter, and the 20th letter, even if all these numbers are less than 26, it's gibberish because this matrix scrambles things up. Shucks, you have 34. Like, my goodness, what is the 34th letter of the alphabet? But remember, if I call this A times B equals C, I can find out what B is. If I know A times B is C, I can find out what B is. All I do is, on both sides of the equation, on the left-hand side of both sides of the equation, I multiply by A inverse. And A inverse times A is identity matrix. And identity matrix times B is just B. And the right side is A inverse C. Oh, you mean the matrix that I want the person to ultimately have is A inverse times C. They have C. You mailed them C. All you have to do is also tell them the day before, hey, John, or hey, Julio, here's A inverse. Don't tell anyone A inverse. Don't tell anyone A inverse. So you encoded the message, and then by multiplying on the left by this matrix A, you coded matrix B, which easily translates to math is fun, and you multiplied it on the left by A, and you emailed it to your friend, and they received the matrix at the right. Now, all your friend has to do is take that matrix that he or she received and multiply by A inverse. 34, 36, 41, 21, 28, 35, 33, 27, and 20. Now, they have to multiply by A inverse. And I actually did that. I actually computed the inverse of that matrix. Some things I actually have to prepare. The inverse of that matrix is this matrix. And I was about to multiply these two matrices, but I know what I'm going to get. I'm going to get that matrix B. 13, 8, 6, 1, 9, 21, 20, 19, and 14. So now the person you sent your email to, the receiver, now has this matrix. And what they do is you tell them beforehand. That's the first, that's the first letter, that's the second letter, that's the third letter, the fourth, the fifth, the sixth letter. And they say, well, letter 13 is M, letter 1 is A, the 20th letter in our alphabet is T, the 8th letter is H, the next letter is I, the next letter is S, the 6th letter is F, the 21st letter is U, the 14th letter is N. And then they're going to have to know to partition it this way. Math is fun. Because it's not going to be that way. They're just going to have M-A-T-H-I-S-F-U-N. And they're going to have to realize to split it there. So this is pretty neat. Now, if somebody tries to intercept this email, that is, they receive this. They receive that. I guess that they could eventually decode it. But what they're going to have to do is take that matrix and multiply it by every invertible matrix. Every matrix, every 3 by 3 matrix that has an inverse. And you know what? That might not even work. You know why? We could have put the matrix on the other side. We could have put the matrix on the other side. So when they get this message, they would have to multiply the inverse on the right-hand side. There are, I suspect, there are an infinite number of 3 by 3 matrices. They're going to have to try every one of them. My advice is don't use numbers that just 0. Use numbers like that have the square root of 7 and cube and log of 11, and I guarantee you they're not going to figure that out. They're not going to figure it out. So I always wonder how people break code, because I really believe you're not going to break this code. And if I'm wrong, please send me an email telling me how to break that code. I'll be more than thrilled to read your argument. But with high-power computers, you can have it in some logical order. Check or multiply this received message that you sent in the email on the left and the right by every invertible 3 by 3 matrix. And I would think that would take a while. And if you do come up with a scheme where you can figure it out, well then I'll make it even harder. Instead of doing 3 by 3, how about we send a message 25. You can play games that way. Okay. The next and last thing that one typically talks about in this section is rotation. Suppose you have a point P, which is at xy. Now, point P and vector u are very similar. They both end at point P. Now, in this angle, this vector u has an angle off the x-axis. Call it angle theta. Now, if you were to rotate this point counterclockwise to this point here, which I'll call P prime, which is x prime, y prime. And I'll call this vector over here u prime. Now, the lengths of u prime and u are the same. Oh, and you rotated it degrees. U and u prime, vector u and vector v, they have the same lengths. I mean, after all, you're rotating from the origin. It's like a circle. Take a compass, put the needle down there, open it up to some distance, and go around. Now, maybe we went from that point right here to the point over here. Well, if that's the case, those two distances are the same. These vectors have the same lengths. Okay. And let us call that length r. Let us call the length r. So, of course, what I want to find out is if you have the point xy and you rotate it counterclockwise 3 degrees, what is the point x prime, y prime? This is a linear transformation. I want to take L of that point, and I want to get point P prime. Okay, so now, this is some matrix times x prime, y prime. And what we're going to do is we are going to find that matrix. So here, it's a linear transformation. A matrix A times a vector is a linear transformation. And I'm not saying you should always think of it that way, but it is. All right, so let us draw this little diagram, the one at the bottom, but only part of it. Just the bottom half. This here is P, which is xy, and I'm saying that the length of u is r. Well, this is a right angle. Since the y value is y, this height is y, and this is x, and that's theta. So we know that the cosine of theta is adjacent over r, over hypotenuse. Let me put the x here. So the cosine of theta, is x over r. But the over r I can put up there. If x over r is cosine theta, I multiply both sides by r, and basically that r in the bottom just goes right up there. X is r cosine theta. And if you look at the sine of theta, the sine of theta is opposite theta is y over r. It's y over r. But the r I'll put on the other side. Okay. And we have these two. Going to hold on to them like never before. And since we have two different angles, let that look very much like theta. Because it is. Okay. Now, when you get rid of that diagram at the top left, and we put back the new diagram. This time, I'm going to concentrate on the point P prime. First, I concentrated on the point P. Now, P. You have the x-axis, you have the y-axis, and you have this vector, a p prime. X prime, comma, y prime. What is this angle? Well, let's look at the lower graph. Never really touched that one, nor will we. It's theta vector prime is theta plus, it's theta plus phi. Okay, I mean, it is what it is. And if I drop this, since that's y prime, then this length is y prime, and this is x prime. And the radius, the length of vector u prime, is the same as the length of vector u, which I'm claiming is r. Okay. So now, what is x prime? That is, what is the cosine of theta plus phi? Well, the cosine is x prime. I'll just put the r on the other side. And now, y prime is, well, let me not state that yet. The sine of theta plus phi is, the sine is adjacent. Sorry, the sign is opposite. Over r. Well, the over r just comes up there. Just the way life is. The y prime goes up there. I meant to say the r. Okay. Now, we are going to use the sum rules. What is the sine, what is the cosine of a sum of angles? And that's what we're going to do. So, x prime is r times the cosine of theta plus phi. Well, let me think. So this is cosine theta times the cosine of phi minus the sine of theta times the sine of phi. But that r, I'm going to distribute. The r in front, I'm just going to distribute. That is, I get r cosine theta, cosine phi minus r sine theta, sine phi. Okay. Now, I want to write this line a little bit lower because I need some more space. So let's do that. And now, I don't want to have anything that has thetas. I don't want to have anything that has theta. Why? Because when I have point P, when I have point P at the bottom, I don't want to know what that angle is. I just want to say, hey, I have point P and I rotated theta degrees. What's that new point? I don't want to have to figure out what angle theta is. All right. So now I know one thing. It's right above. It tells me this. R cosine theta is x. Okay. So I get x times cosine of phi minus r sine theta. Oh, r sine theta. Oh, that's y. Y sine phi. Let's make that look like a phi like never before. Okay. Now, let's play the same game with y prime. Because now I have x, just in terms of phis. Okay. What is sine of a plus b? That is, what is sine of theta plus phi? So y prime is equal to r times that. Well, this is the sine of the first angle times the cosine of the second angle, phi, plus the sine of the second angle times, you know, I don't want to write it that way. It's not wrong, but I don't want to write it that way. Multiplication commutes, so it's no big deal. Cosine of phi, nope, cosine of theta, that's the order I wanted. Cosine of theta times the sine of phi. It's just a trigonometric identity that students need to know. Distributing the r, y prime is r sine theta cosine phi plus r cosine theta sine phi. R sine theta is y. So I get y times cosine theta, I meant to say cosine phi, plus r cosine theta is x. So I get x sine phi. And this is addition, and I want to permute them because I want x first. So y prime is x sine phi plus y cosine phi. Okay. So I have x prime right here, and I have y prime right here. And I'm going to erase a lot, and I'm just going to put that down. Just going to put that down. I have that, this one. I have x prime is x cosine theta minus, I meant to say phi, minus y sine of phi. And from the bottom, very bottom, y prime is x sine phi plus y cosine phi. Okay, let's erase all of this stuff. Need that space. Now remember, I want to know what x prime, y prime is. That's all I want to know. You tell me the angle that you want me to rotate. You tell me x and y, and I want x prime, y prime. Oh, you mean that's all you want? Well, that's pretty easy. X prime, y prime as a vector is cosine phi, sine, negative sine phi. Notice I have the x's, the x terms lined up, and the y terms lined up. Sine phi, cosine phi. And if you multiply this matrix by the point xy, you get this. You get that, which in turn is x prime, y prime. So that's how you find x prime, y prime. If you have the point 2, 3, and you want to rotate it, 90 degrees. Remember, the sine of 90 degrees is 0, and the cosine of 90 degrees, the sine of 90 degrees is 1, excuse me, and the cosine of 90 degrees is 0. So, x prime, y prime, it's going to equal to the cosine of 90 degrees is 0. So both of those are 0. And the sine of 90 degrees is 1, and this will be negative 1. And the point that we have is 2, 3. And if you actually did the matrix multiplication, you would get negative 3, 2. Okay, there it is. There it is. In fact, what if instead, let's prove a little theorem while we're at it. Let us take the point AB. Suppose we have the point AB. If we multiply that special matrix by AB, let's see what we get. Let's see what we get. We get negative B, A. Oh, you mean if you have the point 74, the first entry becomes the second entry, and the second entry, the 4, becomes the first, but the sign changed. You interchange these two, and when you move this one over, you change the sign. When you move the 7 over, you don't change the sign. We just proved something major, that if you have the point 7, 2, or, 8, 2, and you rotate it 90 degrees, you rotate this 90 degrees, this point will be negative 2, 8. I switch the 8 into 2, and the 2, when I move it, the sign changes. If you rotate the point 8, 2, 90 degrees, you switch these two, and whatever that number is, when it comes over, you change the sign. It's negative 2, 8. And we actually just proved that. Right. Now, how about we do one theoretical exercise, and that will complete this section. If in a linear transformation, you come to know that L of U is the 0 vector, and L of V is the 0 vector, then L of any linear combination of U and V will also be the 0 vector. That is, let R and S be scalars. Then L of RU plus SV is also the 0 vector. So, show that if L of U equals 0 and L of V equals 0, then for any scalars R and S, we have make a linear combination of times U is also going to be 0. Okay. L of RU plus SV by our theorem. This is L of the first, but their R can come out in front, plus L of the second, L of SV, but the S can come out in front. And we know that L of U is a 0 vector, which gets multiplied by R. And L of V is a 0 vector, which gets multiplied by S. And if you have the 0 vector, say in R3, and you multiply it by the scalar pi. Pi times 0 is 0. Pi times 0 is 0. Pi times 0 is 0. So you're back to the 0 vector. That is, r times the 0 vector is a 0 vector. S times the 0 vector is the 0 vector. You add the 0 vector, you get the 0 vector. That completes the proof. It also completes this section on Introduction to Linear Transformations.